Its 36-year mission has focused on exploring strange new universes, seeking out peculiar phenomena, grandiose beams, and new plasmas, and venturing into regions where no spacecraft has gone before. Explorer 1 has been traveling through space for over 4 decades, significantly exceeding its original mission. Initially designed to last just a few years, it has defied expectations and achieved remarkable milestones. Recently, Explorer 1 detected unknown objects passing through space, a discovery that has reshaped our understanding of the universe. This plasma originates from the explosions of massive stars that occurred millions of years ago and carries with it the magnetic field of the cosmos. Join us as we delve into these unexplored cosmic entities and examine how they may forever change our perspective on historical data. For several years, our focus has primarily been on data from within the solar system. However, thanks to Explorer 1, we now have access to information from beyond it. In August 2012, Explorer 1 officially completed its journey through the solar system and crossed the heliopause. This was no easy feat. As the spacecraft ventured further from the Sun, the amount of sunlight available to power its instruments diminished significantly. The spacecraft's power is primarily generated by 3 radioisotope thermoelectric generators, RTGs, which convert heat produced by the natural decay of plutonium-238 into electricity. Over time, the declining heat output of the RTGs has led to a reduction in available power, impacting the operation of various onboard systems, including scientific instruments and communication capabilities. To conserve energy, certain non-essential systems and instruments have been deactivated or placed in a dormant state. If the spacecraft continues to operate, it may not be as effective as before. The vast distance between Explorer 1 and Earth also poses a significant challenge for maintaining effective communication. As the spacecraft entered interstellar space, the strength of the signal weakened considerably, taking over 21 hours for signals to travel from Explorer 1 to Earth. This weak signal, combined with interference from background noise, creates a major obstacle to efficient data transmission and collection. Additionally, there are temperature challenges. Transitioning from the heliosphere to interstellar space exposes Explorer 1 to extreme temperature variations. While it was closer to the Sun in the heliosphere and experienced higher temperatures, it now faces extremely low temperatures in interstellar space, which can affect the spacecraft's materials, electronic components, and systems. Thermal stress and cycles of expansion and contraction can impact the structural integrity of certain parts, and extreme cold can make materials brittle, potentially leading to cracks or degradation of seals and connectors. These temperature fluctuations also influence the performance of the RTGs, which are designed to operate within specific thermal ranges. Cooling of the RTGs reduces power output, exacerbating the power challenges. Interstellar space is not entirely empty. It contains a sparse distribution of dust particles. Although these particles are small, they can pose a threat to Explorer 1. When the spacecraft encounters interstellar dust, the particles can collide with its exterior surfaces, causing wear and tear on protective coatings, antenna surfaces, or other sensitive areas. Dust accumulation on the optics or sensors of the instruments can impair their functionality, degrading data quality. Explorer 1 is equipped with a dust detector instrument specifically designed to measure the density of interstellar dust. Moreover, NASA's global network of antennas for communicating with deep space missions has limited resources for receiving signals from Explorer 1, making communication opportunities less frequent than before. Amid the flow of data, an intriguing revelation emerged. Explorer 1 detected an unusual anomaly with a substantial number of signals, most of which were challenging to interpret. However, one signal indicated the presence of 300 known objects passing through the vast expanse of space. These mysterious entities originating from the depths of interstellar space left scientists worldwide astonished. The discovery of these 300 unidentified objects challenges our understanding of the universe. Are they remnants of ancient celestial bodies, drifting relics from distant star systems, or do they signify the existence of previously unknown phenomena? Usually, the data sent by Explorer is relatively easy to interpret, but this particular information was scrambled. While numerous questions arose, answers remained elusive. However, things took an unexpected turn. Despite the curious nature of the transmitted data, Explorer 1 itself appeared to be functioning well. Remarkably, its communication link with Earth remained intact, allowing crucial data to be transmitted to NASA without significant issues. Investigations revealed that none of the spacecraft's protective systems had been triggered, indicating it had not entered a protective mode, which would typically occur if any threats were detected. Therefore, it was clear that Explorer 1 was not under attack. But what could be causing the telemetry data to appear scrambled or erroneous? Was it due to interference from cosmic phenomena like radiation or high-energy particles, or could an entirely unknown factor be affecting the situation? To ascertain the truth, a meticulous investigation into a wide range of potential causes was necessary. NASA's research team carefully examined the spacecraft systems, considering the effects of cosmic radiation on electronic components and the possibility of temperature changes impacting the stability of its sensitive instruments. There was a chance that something had occurred just before Explorer reached the heliosphere, and the usual challenges encountered during the journey had led to data scrambling. However, the only issue was that it was not in an environment where the typical difficulties were expected to pose a danger. The team also analyzed the complexities of Explorer 1's communication systems, investigating potential signal distortions caused by cosmic noise interference or subtle changes in its trajectory. The quest for answers led the team to meticulously analyze potential factors affecting the spacecraft's operations. They scrutinized the impact of cosmic radiation on electronic components and examined the possibility of temperature fluctuations influencing the stability of its sensitive instruments. While this process may seem routine, the implications are profound. The research that led to this breakthrough took a considerable amount of time. The team employed advanced data processing techniques and developed innovative algorithms to replicate various scenarios, ultimately isolating the root cause of the unusual telemetry anomalies. This approach was essential for identifying the source of the problems and ensuring that their efforts were not in vain. After enduring years of receiving confusing data from the spacecraft, the engineers finally managed to restore clarity and reliability to the information streaming in from the far reaches of interstellar space. The primary issue was traced back to Voyager 1's Attitude Control System, ACS, specifically a malfunctioning onboard computer that had been inactive for years, which caused the degradation of transmitted data. Despite this setback, the rest of the spacecraft continued to function properly and carried on with its data collection activities. Upon discovering the source of the problem, engineers quickly devised a solution. They sent a command to Voyager 1 instructing its ACS to switch to the correct computer for transmitting telemetry data. Although this fix was relatively straightforward, it required immense patience due to the significant time delay caused by the vast distance between Earth and Voyager 1, with radio signals taking nearly 22 hours to travel. Adjusting the troubleshooting process demanded extreme coordination, especially considering that Voyager 1 was constructed many years ago and had been functioning smoothly until this incident. Engineers had to consult manuals from the 1970s to get to the bottom of the issue. After thorough evaluation, they identified a simple and safe solution. By resetting the system responsible for data transmission, they were able to rectify the problem without disrupting other spacecraft components. The expertise and dedication of the engineers played a crucial role in successfully restoring the clarity of Voyager 1's communication stream. Their efforts underscored the importance of leveraging historical data in conjunction with modern technology to overcome challenges in space exploration. Experts suspect that Voyager 1's shift to the non-functional computer was triggered by a faulty command received from another onboard system, indicating a deeper issue within the spacecraft's intricate computer network. Despite these concerns, mission leaders remained cautiously optimistic, emphasizing that the incident did not pose a significant threat to Voyager 1's long-term success. In fact, Voyager 1 continued its mission, having successfully passed through the heliopause, the boundary marking the outer limits of our solar system, where the solar wind reaches the interstellar medium, defining the edge of the heliosphere. This boundary lies approximately 123 astronomical units from the Sun, roughly equivalent to an astonishing 11 billion miles. The heliopause is unique, with its shape influenced by changes in interstellar gas and the solar wind generated by the Sun's movement through space. As the Sun travels, it creates a magnetic bubble or sheath within this boundary, shaping the heliosphere's outer region. This magnetic envelope contributes to the complex structure and behavior of the heliopause. When Voyager 1 and future spacecraft cross this boundary, several phenomena occur. Notably, there is a marked decrease in the temperature of solar wind-charged particles as the spacecraft moves beyond the influence of the Sun's direct emissions. This change alone could render many spacecraft ineffective, but Voyager 1 persevered. Moreover, a shift in the direction of the magnetic field occurs, reflecting the altered impact of interstellar magnetic forces. Additionally, there is a significant increase in the presence of cosmic rays, high-energy particles from distant sources, becoming more pronounced beyond the heliopause. Voyager 1's journey marked a historic achievement, offering humanity its first glimpse into the unknown realms beyond the heliopause and shedding light on the transition from solar influence to deep space. In November 2018, Voyager 2 followed in its predecessor's footsteps, crossing the heliopause and venturing into interstellar space. This significant accomplishment opened a new chapter in our understanding of the boundary between the solar system and the interstellar medium. Voyager 2's passage through the heliopause provided scientists with a unique opportunity to compare and contrast observations made by both spacecraft, further expanding our knowledge of this uncharted territory. As Voyager 2 journeyed beyond the heliopause, it made intriguing discoveries that enriched our understanding of this overlooked region. One notable observation was a sharp increase in the intensity of low-energy particles, a direct consequence of exiting the Sun's influence. Voyager 2 also detected a simultaneous rise in the strength of high-energy cosmic rays originating from distant sources. Unlike Voyager 1, which encountered precursor events prior to its exit from the heliosphere, Voyager 2 experienced a different scenario, revealing the existence of a distinct boundary layer located just beyond the heliopause. In this boundary layer, low-energy particles flowed outward along the Milky Way, illustrating the complex dynamics at the interface between our solar system and the interstellar medium. Overall, this surprising observation highlighted the intricacies of the interstellar boundary and the unpredictability of its characteristics. Despite the apparent similarities between the two spacecraft, their distinct experiences raise questions about the potential variations for other probes traversing the same region. With NASA's commitment to understanding the heliosphere and beyond, the interstellar probe represents an ambitious initiative to gather comprehensive data and insights into the prevailing conditions throughout the heliosphere and the heliosheath. It's important to note that there is a difference between the heliosphere, the area influenced by the solar wind, and the heliosheath, the outer layer of the Sun's magnetic bubble. Equipped with advanced technology, the interstellar probe marks a significant leap forward in interstellar exploration. Proposed in 2018 by NASA's Applied Physics Laboratory, this ambitious mission aims to launch the probe between 2036 and 2041, embarking on a journey that will span many years and cover hundreds of astronomical units from Earth.